Welcome, students. Today, we delve into an intriguing challenge that combines analytical thinking with practical application in the realm of finance. We will be exploring LeetCode Problem 121, titled Best Time to Buy and Sell Stock. The essence of this problem lies in determining the maximum profit one can achieve from buying and selling a stock, given a sequence of prices over a series of days. Imagine you have an array of integers, where each integer signifies the stock price on a specific day. Your objective is to identify the optimal buying and selling points to maximize your profit. For instance, consider the input array 7, 1, 5, 3, 6, 4. Here, the most strategic choice is to purchase the stock on day 2 when the price is at its lowest, 1, and subsequently sell it on day 5 when it peaks at 6. This yields a maximum profit of 5. If the data indicates no profitable opportunities, the output should simply be 0. As we embark on solving this problem, let us sharpen our analytical skills and apply effective strategies to uncover the solution. The two pointers technique is a powerful strategy used in solving problems involving arrays and linked lists. Imagine you have a long queue of people, and you want to find two specific individuals who meet certain criteria. By using two pointers, you can effectively traverse this queue from both ends, allowing you to efficiently pinpoint the pair you're looking for. This method starts by placing one pointer at the beginning and the other at the end of your data structure. As these pointers move, one forward and the other backward, they evaluate the elements they point to, checking for conditions that meet your requirements. By doing this, you can often reduce the time it takes to find a solution, shifting from a slower quadratic approach to a much faster linear one. The beauty of the two pointers technique lies in its simplicity and effectiveness. It helps streamline processes like merging sorted lists or searching for pairs, making it a fundamental tool for any computer scientist. Understanding this technique not only enhances your problem-solving skills, but also prepares you for more complex algorithms in the future. To find pairs that sum to a specific target value, we can use the two pointers technique, which is efficient and straightforward. First, we sort the array. This sorting step is crucial, as it allows us to effectively use two pointers to find our pairs. Next, we initialize our two pointers, one at the beginning of the array and the other at the end. As we loop through our array, we calculate the sum of the values at these two pointers. If the sum equals our target, we've found a valid pair, so we store it and then move both pointers inward to continue searching. If the current sum is less than our target, we need a larger number, so we move the left pointer to the right. Conversely, if the sum is greater than the target, we move the right pointer to the left to decrease the sum. This way, we efficiently explore possible pairs without needing to check every combination, making our solution faster. Finally, we return all the pairs we found. Maximum profit tracking is all about finding the best times to buy and sell assets, like stocks, to achieve the highest possible profit. Imagine you're at a market and you want to buy apples. You want to buy when the price is low and sell when it's high. This is the essence of maximum profit tracking. In finance and economics, this concept helps investors make decisions that can lead to significant financial gains. By analyzing prices over time, one can identify the optimal moments for transactions. For example, if you know a stock's price tends to rise after a certain event, you can plan your buy and sell strategy around that. To do this effectively, various algorithms are used. Techniques like dynamic programming and greedy algorithms analyze past data to spot trends and predict future prices. This helps in minimizing risk while maximizing profit. Understanding this concept equips you to make informed decisions, whether in trading or managing resources, ultimately leading to better outcomes in uncertain environments. In this slide, we have a function designed to track the maximum profit from a list of stock prices, which is a common problem in finance. The function starts by initializing two key variables. First, it sets min price to infinity. This means we are looking for the lowest price we've seen, and starting with infinity ensures that any price we encounter will be lower. Next, max profit is initialized to 0 because initially we haven't made any profit. As we loop through each price in the list, we continuously check if the current price is lower than our min price. If it is, we update min price to this new lower value. Then we calculate the potential profit by subtracting min price from the current price. If this current profit is greater than our recorded max profit, we update that as well. Finally, after checking all prices, the function returns the maximum profit found. This approach efficiently finds the best time to buy and sell stocks, giving you the insights needed to make informed financial decisions. The concept of a linear scan of prices is a fundamental technique in algorithm design that allows us to analyze a list of prices in a straightforward way. Imagine you're looking through a stack of receipts, one by one, to find the lowest price you paid. This is similar to how a linear scan works. You start at the beginning of the list and systematically check each price until you reach the end. In a linear scan, we keep track of important information, like the lowest price or the total of all prices, by comparing each price to what we've already noted. This method operates efficiently with a time complexity of O(n), meaning that if we have n prices, we'll look at each one just once. This technique is particularly useful in various fields like finance, where understanding price trends is crucial. By using a linear scan, we can quickly gather insights without the need for complicated algorithms, reinforcing our understanding of fundamental programming concepts like loops and conditionals. In essence, it's a powerful yet simple tool to help us make sense of data effectively. The function shown on this slide is designed to double the prices from a list. First, it initializes an empty list called doubled to store the new values. This is like setting up a container before we start filling it with items. Next, it uses a loop to go through each price in the input list, prices. Think of this as looking at each item on a shelf one by one. For every price, the function multiplies it by 2, effectively doubling its value, and then adds that new value to our doubled list. Finally, the function returns the list of doubled prices. For example, if we input a list like 10, 20, 30, the output will be 20, 40, 60. This straightforward approach is efficient and easy to understand, making it a great example of how to work with lists in programming. To solve the LeetCode problem of finding the best time to buy and sell stock, we follow a straightforward algorithm. First, we need to understand that our goal is to maximize profit, which means we want to buy at a lower price and sell at a higher price later. We start by initializing two key variables: min price, which we set to a very large number, and max profit, initialized to 0. This helps us track the lowest price we've encountered so far and the maximum profit we can achieve. Next, we loop through each price in the provided array. For each price, we check if it's lower than our min price and update it if it is. Then we calculate the potential profit by subtracting min price from the current price. If this potential profit is greater than our recorded max score profit, we update max profit. Finally, after checking all prices, we return max profit, representing our maximum achievable profit. This algorithm runs efficiently in O(n) time since we only need a single pass through the prices, making it suitable for large data sets. The space complexity remains O(1) since we only use a couple of extra variables. Here is a simple Python implementation of this logic. Python def max profit prices, min price equals float inf, max profit equals 0. For price in prices, if price min price equals price potential profit equals price minus min price. If potential profit max profit equals potential profit, return max profit. By following these steps, we efficiently determine the maximum profit from the given stock prices. In this problem, we are tasked with determining the maximum profit achievable from stock prices represented by an integer array. Each element reflects the stock's price on a specific day, and the key requirement is to buy before selling. Notably, the input array will contain between 1 and 100,000 elements, with each price ranging from 0 to 10,000. These constraints will significantly influence our approach to formulating an efficient solution. Let us explore the methods to tackle this challenge. The provided Python code addresses LeetCode problem 121, focusing on calculating the maximum profit from stock prices, with the key requirement that you must buy before selling. The algorithm operates with a linear time complexity of O(n), making it efficient for large datasets. In the function maxProfitPrices, we start by initializing two variables, min price set to positive infinity and max profit initialized to 0. By using infinity for min price, we ensure that any stock price we encounter will be lower, allowing us to easily find the lowest price. As we iterate through each price in the prices list, we check if the current price is lower than min price. If it is, we update min price to this new lower value. This ensures we always have the minimum price up to the current point. Next, we calculate the potential profit by selling at the current price. If this profit exceeds our recorded max profit, we update it. This simple yet powerful strategy embodies the core principle of trading: buy low, sell high. The algorithm requires only a single pass through the data, using a constant amount of extra space, showcasing an efficient approach to solving this problem. In this problem, we're analyzing the time and space complexity of finding the best time to buy and sell stock. The time complexity is ON. This means that we need to look at each element in our array of stock prices exactly once. Think of it like walking down a row of houses to find the best deal on a car. You can only compare prices by checking each house individually, which takes time proportional to the number of houses, or in our case, stock prices. Next, we have a space complexity of O1. This indicates that our solution doesn't need to use extra space that grows with the input size. We only need a couple of variables to keep track of the minimum price we've seen so far and the maximum profit we can achieve. It's like carrying a small notebook. No matter how many houses you check, you only need one notebook to jot down your notes. By understanding these complexities, we can appreciate the efficiency of our solution.